Okay, so here's section 4.5, question 6. Consider this function f of x is 3x plus 5 over 4x plus 1. For this function, there are two important intervals where the function is not defined at a. So you're basically finding the value a where f is undefined. So what we're doing with these intervals is essentially finding the domain. Okay, so to find the domain, what we want to do is figure out where the denominator is not equal to 0. So the denominator is 4x plus 1. So we'll start by setting 4x plus 1 equal to 0 and solve. Okay, so I get negative 1/4. So that should be the value for a. Okay, for each of the following intervals, tell whether f is increasing or decreasing. So on negative infinity to negative 1/4, is it increasing or decreasing? So what we're going to do here is the first derivative test. So I'm going to start by finding the first derivative of the function. Okay, and what we're going to do is use the quotient rule. So the derivative of the top times the bottom left alone minus the top times the derivative of the bottom all over the bottom squared. And in the past, I've told you you don't have to bother simplifying derivatives, but I think because we're going to be using this, it's going to be worth our time to simplify the derivative as much as possible. So I'm going to distribute that 3, so we get 12x plus 3. Here I have a negative and a 4, so I'll distribute it as a negative 4. So I have minus 12x minus 20. The bottom is already fully simplified. Factored form is simpler than expanded out. Okay, so 12x minus 12x adds to 0. 3 minus 20 is negative 17. Okay, now when I look at this, no matter what I plug in for x, as long as I get a number, the denominator is going to be positive. The numerator is going to be negative. So it really doesn't matter which side of negative 1/4 I'm on. I know I'm going to get a negative over a positive or a negative. Okay, so this is going to be decreasing on both sides. Okay, but sort of the longer way to look at that is to say here's that negative 1/4. I'm going to test a number from each side to see if it's positive or negative in the derivative, which tells me if it's increasing or decreasing. Okay, next, this function has no inflection points, but we can still talk about its concavity. So let's look at the concavity. We repeat the same process except with the second derivative. So I'm going to start by finding f double prime. Now, in order to find f double prime, I'm going to back up one quick second here. And instead of using the quotient rule, if I rewrite this as negative 17 times 4x plus 1 to the negative 2, then I can just use the chain rule to find the derivative. So the negative 2 comes down, the double negative will make it a positive 34. 4x plus 1 stays the same, lower the power by 1, and then multiply by the derivative of the inside stuff. Okay, so let's multiply 34 times 4. I think that's 136. And then we'll put this 4x plus 1 cubed in the denominator as a positive power. So there's a simplified second derivative. So if I repeat the same thing, I have my negative 1/4. Okay, there's no new critical points for the second derivative. What I'm going to do is test a number from each side. So f double prime of 0, that would be on the right side, will give me 136 over 1 cubed, which is 136. That's positive, so it's concave up. And if I plug in something less than negative 1/4, say a negative 1, so 4 times negative 1 is negative 4, plus 1 is negative 3, cubed. It doesn't really matter exactly what the value of this number is. I know that when I cube a negative, I'm going to get a negative. Positive over a negative is negative, so this is going to be concave down. Okay, so it's concave down to the left of negative 1/4 and concave up to the right. All right, does that make sense?
Yeah, it does. Thank you.
Okay, another homework question? So maybe what it might be worthwhile to go through. So the quiz is looking at questions from 4.1, 4.3, and 4.5. Maybe since we just did an example of a question on 4.5, let me go through an example that might be something like what you'll see on the quiz. Anything from 4.5 is good to look at, but let's just take a look here. Okay, so let's look at an example from 4.5, and I'm just going to kind of make one up here. Okay, so what I want to do since I'm making up a question is to make it different than maybe some of the homework questions, and here's the way in which it's different. You don't actually do a lot of graph sketching on the homework because it's kind of a pain. When you have the homework grade your graph, it can be difficult to, it can be sometimes either too picky or not picky enough. Okay, so most of the homework questions don't have you actually drawing graphs. So I want to make an example where you do have to draw a graph. And what we're going to do for this question is, rather than give you the formula for a function, you're going to be given information about the function. So let's suppose you know that the domain is, say, negative infinity to 2 and 2 to infinity. Let's suppose that you know the y-intercept, okay, is 3. Let's suppose that you know that the derivative is positive. On negative infinity to negative 4 and 5 to infinity. Let's suppose that the derivative, first derivative still, is negative negative 4 to 2 and 2 to 5. I gotta be careful here. I'm gonna run myself into a problem. One quick second. Okay, so here's some information about the first and second derivative, the y-intercept and the domain. We want to sketch a graph of the function. So here's how we can go about this. Here's the axes where I'm going to draw my graph, and underneath that I'm going to put in a number line and put all the information for my first and second derivative on there. Okay, where everything is labeled like the x values line up, right? So if here's 2 on my graph, here's 2 on my number line. Okay, other important numbers are -4, -6. Okay, and as far as x values, and then a 5. Okay, so what I'm going to do is on this number line below, I'm going to label all of the increasing and decreasing on each of these intervals. Okay, so when f prime is positive, the function is increasing. That goes from -infinity to -4, so it's going to be increasing on both of these pieces. And then from 5 to infinity, it's increasing. It's decreasing on -4 to 2, and from 2 to 5. Okay, for the concavity, f double prime being positive means it's concave up. So that goes concave up from -infinity to -6, and then from 2 to infinity. So that means 2 to 5 and 5 to infinity. And then it's concave down on -6 to 2, so on both of these intervals. Okay, when we go to sketch the graph, we want to put in the point that we know, right, 0, 3. So I'll suppose here's 3. Okay. And 2 is not in the domain, so maybe I have a vertical asymptote, maybe I don't know. I'll just draw in a vertical asymptote because I know that that'll work. And then what we need to do is make sure that we meet all of these increasing, decreasing concavity criteria. So I'm going to start with the point on the graph that I know. On this interval, it is concave down, but decreasing. So if I draw concave down and I draw the decreasing side, I just get something that looks like this. And on the right side, it has to approach my asymptote because I drew in an asymptote. So I'm going to get something like this. Okay, we'll just continue on from the left. On this -6 to -4 interval, it's concave down, but increasing. So I want the increasing side. Okay, so I'm going to get a piece that looks maybe like this. Okay, -infinity to -6, it's increasing, but it's concave up. So I'm going to get the increasing side of concave up, and I want to connect that up with my graph. Okay, to the right of the asymptote, it's concave up and decreasing, so I draw the decreasing side of concave up. That's the shape that I want. Oops. And I want the graph to approach my asymptote because I drew one in there. Okay, and from 5 to infinity, it's concave up still. I want the increasing side of concave up. Okay, so this would be an example of a graph that meets all of these criteria, and that's, I think, an organized process for how to sketch a graph like that. It's not something that you find as much in the homework, but it's something that, maybe we look at a little bit in class, and it's, the type of form that you might see on an exam because it requires a lot less computing and simplifying derivatives than, say, the homework question that we just looked at. All right, any other homework questions you want to take a look at?
Yes. 4.5, number 16.
Okay, so we're going to do 4, 5, number 16, but I got another question. How do you know which is concave up or down? So when the second derivative is positive, then the function is going to be concave up. When the second derivative is negative, it's going to be concave down. Okay, so concave up is like a cup facing up. Concave down is like a cup facing down. Okay, so I labeled those on the intervals that I had, and kind of went from there. Does that make sense? All right, and then I think we said, did you say 4.5, number 16?
Yes.
All right, consider a third degree polynomial f of x which has the properties f prime of 2 is 0 and f prime of 3 is 0. Okay, so if f prime of 2 is 0 and f prime of 3 is 0, then on these intervals the function's either going to be increasing or decreasing. Okay. Normally we would say like anything is possible. Although with polynomials things are not, they're not quite as random. Because this is a third degree polynomial, I know its derivative is second degree, so it can only have at most 2 zeros. Okay, and since I can see that it has 2 zeros, well, let's just go through and answer the questions. We'll see what we need to figure out as we go. All right, f of x equals 0 for some x in between 2 and 3. Does this have to happen? Well, if all I know is the information about the derivative, right, I can draw a graph of a third degree polynomial that is definitely not 0 between 2 and 3. Okay, so that one's definitely false. Okay, f double prime is 0 for some x between 2 and 3. That's an interesting one. Now, let's think about this as functions. Think of f prime as being your function. So f prime is 0 at 2, f prime is 0 at 3. So either the graph of y equals f prime of x, so in between maybe it goes up and comes back down, or maybe it goes down and comes back up. But either way, it's got to have a horizontal asymptote in between, which means its derivative is 0. And the derivative of f prime is f double prime. So this one's going to be true. Okay, there is no absolute minimum at x equals 2. There we have to be careful. At x equals 2, I could have a relative minimum, right? I could, if the function, get my pen back real quick. If the function were to go down and come up and go down, I could have a minimum at x equals 2. Okay, but it is a third degree polynomial. So I know that at the extremes, one extreme is going off to infinity and the other one's going off to negative infinity. So a third degree polynomial does not have any absolute maximum or minimum. So false. All right, this one is a little bit complicated. If f has 3 roots, then it has 1 inflection point. Okay, so it's a third degree polynomial, and I already know that it has these 2 different zeros for its derivative. The question is, does it have an inflection, if it has an inflection point, so concavity changes, then it has to have 3 roots. Okay, so let's take a look at this. If it has an inflection point, that means that concavity changes somewhere. Okay, so who knows? Maybe at 4, right? Maybe between 2 and 3. I don't know, but it has some inflection point. Okay. Then it has 3 real roots. Okay. Well, again, what I want to do is look at what would it take for it to have 3 real roots and what would it take for it not to, right? It's a cubic polynomial, so it can certainly have 3 roots. Okay. But if it doesn't have 3 roots, that means that this whole wiggly business happens up here. Well, I just drew an example of a graph that only has 1 real root, and I'm pretty sure I can see an inflection point here because here it's concave down, and then over here it's concave up, And I didn't really do any real work analysis or anything like that. I just sort of drew a picture. This one has an inflection point, but it only has one real root. So I can find an example where this one is false. That must mean it must be false. Oh, I skipped number 4. If 4 has 3 roots, then it has one inflection point. Okay. When I draw the graph that has 3 roots, I can sort of see that it has an inflection point. Does that always have to happen? What would it take for this to not have an inflection point? Okay. Right. So maybe let's look at, is it possible to have a cubic that does not have an inflection point? Okay. Oh, sorry. So let's think about what a cubic polynomial looks like, right? Like ax cubed plus bx squared plus cx plus d, right? So then the first derivative, right, if I differentiate it, right, 3ax squared plus 2bx plus c. The second derivative will be 6ax plus 2b. And this is a line, and a line is always going to have a point where it's 0. Okay, so I know that I'm going to get a place where the second derivative is 0. And I could actually solve for that. Okay, so if I solve 6ax plus 2b equals 0, I get 6ax equals negative 2b. Divide both sides by 6a, and I get x is negative b over 3a. So that's a number where second derivative is going to be 0 for any cubic polynomial I write down, as long as a is not 0. But if a is 0, it's not a cubic. Okay. And it's going to be really hard to find a number to the left and the right to test in there. But this is the equation of a line. So, if I have a line and it hits 0 somewhere, it's going to be positive on one side and negative on the other. So I don't know if this is concave down and then up, or if it's concave, up and then down, or if it's down and then up. But it definitely has to switch at this point. Okay, so I think that it's going to have an inflection point no matter what. Okay. Oh, what happened at 2? There's no absolute minimum at x equals 2. Oh, I'm sorry. There is no minimum. It's true that there's no minimum. We just said that the graph will not have a minimum. I didn't read that correctly. I just said it has a minimum. It does not have a minimum. Okay. All right. Does that one make sense?
Yeah, kind of. I think the last two are a bit tricky, but I think I got it a little bit.
Yeah. I agree with you that they're tricky. So I guess for number 4, basically what I was looking at is that if it's a cubic, it has to have an inflection point. There's no other choice because the second derivative is going to be a line. So it's going to have a point where it's 0, and on left and right, it's going to be one side's negative, one positive. So that one's a little bit tricky. Number 5, if it has an inflection point, then it has 3 real roots. Well, we said it always has an inflection point, and we can draw one that doesn't have 3 real roots. So
Okay, so that just kind of like we're kind of using common sense in a way, trying to.
yeah, I mean, it sounds like common sense. In math, though, what we would do is we would say it's a counterexample. So if I say, if I have this statement, if I
Well,
can
yeah.
find one example where it's false, that gives me a counterexample. But you
Hmm.
can't use examples to show that something's true because, to say something's true, it has to always be true, right? So the true ones are harder. The false ones, you can just show a counterexample.
Okay. Actually, can you explain again what's the difference between real roots and just roots? Like, well, I don't really know what
Um,
difference.
yeah, so if I have a graph that looks like this, a cubic polynomial, here there's a real number where the cubic polynomial is equal to 0, and there's only one of them. But if I were to solve this, right, if I had something like let's suppose this was my polynomial. Okay, I can see that when x is 1, I get a root. All right. I would also get a root when x squared plus 1 equals 0, or when x squared is -1. That's not a real number,
Oh, okay.
but it is an imaginary number, right? So if I get imaginary or complex roots, right, then I can have that. So this polynomial actually has 3 roots, but only one of them is a real root, and that's why they say that. But we're not in this class really dealing with complex or imaginary numbers at all. So
Okay, yeah, that makes sense now. Thank you so much.
sure.
I also had two general questions.
Yep.
That's not with the homework.
Okay.
The first one is on my Blackboard. It says that I have two classes. I'm in like two calculus classes. The first one is like W01. By any chance, that was like a mistake, right?
That is a mistake. Are you registered for a W01 or is it just on Blackboard?
It's just on Blackboard. I'm not registered for W01.
Okay. You could, if you look in that Blackboard shell, you could email that teacher and say, I'm not in your class, but I showed up on your your Blackboard showing up on my thing. Can you just remove me?
Okay.
And you can do that, yeah.
Okay then. And also for second question, I guess it's more on the quiz. For the related rates problems, those are probably going to be the ones similar to the one that we did in class, right? Like the area, triangle, or Pythagorean theorem, triangle stuff, and like the shapes, like stuff like that. Those examples.
So in theory, anything is open, but yes, I said in class, and I'll reiterate this. The example on the quiz is going to look like the ones from the worksheet that we were doing in class.
Okay,
or
gotcha.
or at least like one of them, because they're all different from one another. And the idea there is that way you have something I think a little bit concrete to study, and you're not going to feel lost when you see a question that you've never seen before.
Yeah, because yeah, actually, yeah, that makes sense. Okay, yeah, that's all the questions I have. Thank you so much.
Okay. All right. Let's look at section 4.5, question 15. The function f of x equals -2x cubed plus 27x squared minus 84x plus 3. It has one local minimum and one local maximum. Find those. Okay, so what we need to do here is to find local mins and max, we want to find the critical points. So we take the derivative. Okay, so when I differentiate, use the power rule, I get -6x squared plus 54x minus 84. Okay. And I think that I can factor a -6 out of this thing, so that I'll be left with x squared. If I take 54 and I factor out or divide out a -6, I'll be left with a -9. And if I take -84 and I take out a -6 or divide out a -6, I'll be left with +14. Okay, and that just keeps my numbers a little bit smaller. So if I want to find where f prime is equal to 0, we can look at where x squared minus 9x plus 14 is equal to 0. And I think that'll factor into x minus 7, x minus 2. And I get 2 and 7 as my x values. So then I'll put a number line up here, and we're going to test a number from each interval into the derivative. So let's try f prime of 0. I just get -84. That's negative. It's decreasing. I could put 3 in, and I think that the easiest way to do this is just use your calculator, plug into the, the derivative that you have. So I have negative 6 times 3 squared plus 54 times 3 minus 84, and I get 24. That's positive, so it's increasing. And then something bigger than 7. I'll pick 10. So I have negative 600 plus 540 minus 84. And I get negative 144. That's negative, so it's decreasing. Okay, so that means that at x equals 2, I'm going to get a minimum because it's going to go down and come up. And then it says with value blank, so I have to plug that in. If I want that actual value, I'm going to look at the y value. I'm going to look at the original function. Okay, so I'm going to plug 2 into the original function. Okay, and I get negative 73. Okay, if you plug 2 in the derivative, you're just going to get 0, of course. But that's not what it's asking. All right, and then at 7, it goes up and comes down. So at x equals 7, that's where I have a local maximum. And if I plug 7 in to the function, I get 52. Okay. So that's my local max and its y value. Okay, does that one make sense? Okay. Another homework question? All right, 4-5, number 12. Given the function g of x equals 6x cubed minus 27x squared minus 180x, find the first derivative g prime of x. Okay, so let's do that first. So I'm going to differentiate using the power rule. So 3 comes down, so we'll get 18x squared. The 2 comes down, so it's minus 54x, and then minus 180. Okay. Notice that g prime is 0 and x is 5. So what they're doing here is they're telling you what one of the roots is. Okay. Right, so I guess another way to look at that is by telling you that when you plug in 5, you get 0 in the derivative. I know that x minus 5 is a factor here. So that's, in a way, helping me to factor it. So if I want to get an 18x squared, I have to multiply x by 18x. If I want to get a minus 180, I have to multiply negative 5. I could just divide it. Right, 180 divided by 5 is 36. So I have to multiply negative 5 by a positive 36. Okay. And if you wanted to, you could factor from here more. I could take an 18 out. And this would just be an x plus 2. Right? But the point is by giving me one of the factors that helps me factor it. Okay. Now we want to know whether there's a local minimum or maximum at x equals 5, but we're going to use the second derivative test. So instead of making my number line and testing intervals here, what we're going to do is we're going to take the second derivative. Okay, So the 2 comes down, so I get 36x minus 54. Right? And then we're going to plug 5 into the second derivative. So this is the second derivative test, not the test for concavity, though. But if I plug 5 in here, I have 36 times 5 minus 54. I get 126. That's positive. The second derivative is positive, so I know it's concave up there. That means that if I have a critical point, it has to be a minimum. So G double prime of 5 is 126. Based on the sign of this number, it's positive. Does that mean the graph is concave up or concave down? As it's concave up. So because it's concave up, that means that I have a local minimum. Okay, so it turns out for this problem, I didn't have to do any of this factoring bit. That wasn't necessary at all. But what they're doing is they're taking me through the second derivative test. And remember I said we don't really use the second derivative test as often, but it does exist. Here's what it is. Okay, any questions on this one? All right, any other homework questions then? Okay, so let's roll back to 4.1 and look at number 7. So this is good. It's good to look at these. Time for the quiz tomorrow. At noon, Ship A is 50 nautical miles due west of Ship B. Ship A is sailing west at 23 knots, and Ship B is sailing north at 23 knots also. How fast in knots is the distance between the ships changing at 5 p.m.? Note, a knot is in 1 nautical mile per hour. So if we have knots and we have nautical miles, then all the units are nice, and we just, keep in mind that our time is in hours, and we're good to go. All right, so let's start by drawing a diagram. So at noon, Ship A is exactly west of Ship B. So if here's Ship A, it's west of Ship B. So using the normal, north, east, south, west. Ship A is west of Ship B. And this distance is 50. Okay, Ship A is sailing west. Okay, so Ship A is moving this way. So at 5 p.m., it's going to be somewhere further over here. All right, Ship B is sailing north. So at 5 p.m., Ship B is going to be somewhere up here. Okay. So I'm going to write down little a to be the distance that Ship A went during that time. Little b to be the distance that Ship B went. And then I have, maybe I'll call it d for distance between the two ships. So my goal is to find how fast the ships are moving apart. So I want to find dd dt. And I'm given that Ship A is sailing west, so A is increasing, okay, at a rate of 23 knots. So the derivative of A is 23. Likewise, B is increasing, so dB dt is 23. And I want to find out what's going on at 5 o'clock. Well, what's significant about 5 o'clock? At 5 o'clock, ship A has been sailing for 5 hours and it's going 23 knots. So at 5 o'clock, A is going to be 5 hours times 23 nautical miles per hour. And I think that's 115. Should be careful though. Do math in your head. Okay, ship B, same thing. It's been traveling 5 hours at 23 knots. So it's gone 115 nautical miles. Okay. All right, I need to find a relationship between A, B, and D, and I want to use the Pythagorean theorem, but I have to be careful. The triangle that I get, I'll just redraw my triangle and label it. This side is D, this side is little b, this side is A plus 50. Okay, so A plus 50 squared plus B squared equals D squared. Okay. Well, I want to find the rate of change of D, and I have the rates of change of both A and B, so I don't need to eliminate a variable. We can just go ahead and differentiate. So I'm going to start using implicit differentiation on everything. In this first term, we have the chain rule, so I have 2 inside stays the same, multiplied by the derivative of the inside. The derivative of A is dA dt. This is a plus 50, so the 50 on its own when I differentiate gives me a 0. Okay, when I differentiate here, the 2 comes down, inside stays the same to the power of 1, multiplied by the derivative of the inside function. And likewise on the right-hand side, 2 times d times dd dt. All right, now in order to solve for dd dt, I can divide everything by 2, and then divide by d. I need to know A and B, I have both of those. dA dt and dB dt, I have both of those. I don't know D. So before we plug in, I have to find the distance D. So I go back to my Pythagorean theorem and say, okay, at 5 o'clock, what's going on? I have 115 plus 50 squared plus 115 squared equals D squared. So 40,450 equals D squared, and then we square root. So D is approximately 201.122. So I plug everything in. This is a times, not a point. So we end up with the ddt equals 32.0204. And this would be in knots. Okay. All right, so that's 4.1, number 7. Any questions on that one? Okay, another homework question?
Sorry, I just wanted to ask one more thing. For the quiz tomorrow, the three it's gonna cover 4.1,
Yep.
4.3, and 4.5, right?
Yep.
So that's related rates, max and mins, and then the 4.5 one. All
Yep.
right.
The
Okay.
4.5, which is like the graphing. Yep.
Can you give an example of like a max and min problem that like of what we can expect?
Sure. I mean, the max and mins, I think are, the ones from the homework. Let's see. Um, I think are good examples. We didn't go through this section separately in class. Um, okay, so here's a good example. This is 4.3, number 14. Here's a function, find its maximums and minimums, right? So the the process is we first find the critical points. So I'm going to find the derivative. So we're just going to use the power rule. So I get 0 plus 9 minus 36x to the negative 2, and I like to rewrite this. Okay, and actually I'm going to get a common denominator here. Right, multiply by x squared over x squared. Okay, so now I know that f prime is going to be 0 when 9x squared minus 36 is 0. Okay, so we solve that, right? 9x squared equals 36. X squared equals 4. So I get x equals plus or minus root 4, or plus or minus 2. And then f prime is undefined when the denominator is 0. So I get x equals 0. Okay, so I create a number line, negative 2, 0, 2. Test a number from each of these four intervals into the derivative. Okay, so I'll plug in, say, f prime of negative 3. Okay, and I'm just plugging this into the derivative that I have, right? So 9 minus 36 over negative 3 squared. I get 5. That's positive, so it's increasing. Put negative 1 in there. And I get negative 27. It's negative, so the function's decreasing. Put positive 1 in there. Get negative 27, so it's decreasing. And then something bigger than 2, I'll put 3 in there. I get 5, so it's increasing. So 0 is a critical number, but it doesn't change. And also 0 is not defined in the original function, so it couldn't be a max or a min, but it's still an important point when I do my first derivative test. Okay, so I can see that at negative 2, we have a max. And I can see that at positive 2, it goes down and comes up, so we have a min. Okay, and typically with local maxes and mins, we're not as concerned with the y value, but on the off chance that we were, you just plug back into the original function to get the y value. Does that process make sense?
Yeah, it does. And then in the situation where it's asking for the absolute maximum, absolute minimum, that's where you like you take the you take the interval numbers and also find the critical points and then compare them to see which one of the y values are higher or lower, right?
Yeah, so let me, yeah, let's go through an example, why not, um, of absolute maxes and mins. So here's a function, find the absolute max and min on this interval. So typically when we find absolute max and min, it's going to be on a closed interval. And the theorem that we talked about in this section was that if you have a continuous function on a closed interval, you're guaranteed to have both an absolute max and an absolute min. Okay, so I start the same way. We start by finding the critical points, right? So I have 0 minus 8x. Okay, so I figure out where f prime is 0. That's going to be where negative 8x is 0. Okay, and there's nowhere where it's undefined, so I only get 0. I only get one critical point. So then what we do is we create an XY chart. So I'm going to plug my endpoints, -3 and 1 in, and any critical points that fall in between. So 0 falls in between, so I use it. If it so happened, if I had an example where 0 was one critical point and say 2 was another one, I wouldn't use the 2 because it's not in my interval. Okay, now what I do is I'm going to take these three numbers and I'm plugging them into the original function, not into f prime, plugging them into the original function. So when I plug 3 in, sorry, -3, I get 4 minus 4 times -3 squared. -3 squared is 9, times 4 is 36. So we get -32. Okay, when I put 0 into the original function, I get 4. When I put 1 into the original function, I get 0. On this list, the biggest number is 4, so that's the absolute maximum. The smallest number is -32, so that's the absolute minimum. Okay. And if I was answering the questions on the homework, the absolute maximum value is 4. It occurs when x is 0. The absolute minimum value is -32. It occurs when x is -3. Okay, so absolute maxes and mins do work a little bit differently because we're going to build a little table and we're going to check the endpoints also.
Okay, yeah, I completely understand that. Thank you so much.
Sure. Okay, any more homework questions? .5, number 7. Okay, consider the function f of x is 7 times the quantity x minus 4 to the 2/3. For this function, there are two important intervals, right? So basically, we're finding a critical number and then figuring out where it's increasing, decreasing, and then where it's concave up or down. Okay, so I have my f of x, 7 x minus 4 to the 2/3. When I take a derivative, f prime, the 2/3 comes down, so we'll have 14/3 x minus 4. Lower the power by 1, so 2/3 minus 1 is 2/3 minus 3/3, or -1/3, okay, times the derivative of the inside stuff, okay. And if I write this out, maybe in the nice way for doing like algebra stuff, I can put that x minus 4 as a 1/3 power in the denominator. Okay, for doing derivatives, I like it better in this form. So taking another derivative, the -1/3 will come down, and I'll get -14/9 x minus 4, lower the power by 1, multiply by the derivative of the inside stuff. Okay, so there's the first and the second derivative nice and simplified. So if I'm looking for a critical number, I'm going to look for where f prime is equal to 0 or where f prime is undefined. Okay, f prime is going to be 0 when 14 is equal to 0. There's no solution there. 14 is not 0. It's going to be undefined when the denominator is 0. That's going to happen when x minus 4 is equal to 0. So x equals 4 is my only critical point. Okay, so then if I'm doing the first derivative test, we'll make a number line with 4 on it. Oops. Okay. And I'm going to test something from each side of 4 into the first derivative. So I could try something to the left of 4. I like 0 because it's easy to plug in. If I put 0 in, I'm going to have 14 over 3 times negative 4 to the 1/3. And you can use your calculator, or if I just look at this, the cube root of a negative is still negative. Positive over a negative is negative, so I know I'm going to have a negative number here. Okay, but you might be safer off just using your calculator. Okay, and we get negative 2.93. Okay, so I get the negative. All right, something to the right of 4, we can plug in, say, 5. Okay, so then I'm going to have 14 over 3 times 5 minus 4 is 1. Cube root of 1 is 1. I get 14/3. That's a positive number. Okay. So on the interval negative infinity to 4, function is decreasing. And on 4 to infinity, function is increasing. Okay, now we test for concavity. So what I'm going to do is I'm going to look at the second derivative and say, where's the second derivative 0 and where's the second derivative undefined? Okay, so the second derivative is 0 when the numerator is 0, and negative 14 is not 0. Okay, no x values make negative 14 and 0 the same number. It'll be undefined when the denominator is 0, and that happens when x minus 4 is 0, so x equals 4 is the only critical value for my second derivative. So I'm going to test things to the left and right of 4. This time I'm plugging into the second derivative. So when I plug in 0, actually, you know what? I'm not going to plug in 0. 0 is normally nice and easy. But if I plug in 3, I can do this by hand. Because 3 minus 4 is negative 1. Negative 1 to the 4/3 power. If I cube root negative 1, I get a negative. Take it to the 4th power, the negative becomes a positive. So I have negative 14/9. That's a negative, so it's concave down. If I plug in something bigger than 4, try say 5, 5 minus 4 is 1, 1 to any power is 1, so I have negative 14/9. That's also negative. Okay, so it's concave down on both sides of negative 4. Okay, if I wanted to go a step further now and actually graph this thing, it's not required on this question, but if I wanted to use this information to graph it, okay, I would say, okay, it's decreasing and then increasing, it's concave down, concave down. Okay, the other information that we typically try out is getting like a y-intercept. So if I plug in 0 for x, I'll have 7 times negative 4 to the 2/3. okay, which is 17.6. Okay, so I want something that's concave down and decreasing. So this is the decreasing side of concave down. Okay, and then from 4 onward, it's concave down but increasing. Okay, so if I draw that and I hit the same point, I'm going to get a sharp corner here. Okay, so I get a graph that looks like that. Okay, maybe just for our own sanity here, let's go ahead and graph it and see, is this crazy looking graph anywhere close? So I have 7 times x minus 4 to the 2/3 power. And I get a graph. Yeah, I mean, I get basically the same thing, right? Maybe I can zoom out. And you can see, yeah, we get, oops, basically the same graph that we drew. All right. Does that make sense? Okay. Another homework question? Okay, well, if you come up with any questions, feel free to email me. Otherwise, I'm going to shut this down and try to post this up on Blackboard.